So optical mineralogy is a branch of mineralogy, which is very useful for identification of particularly the minerals. Okay, so we will gradually go through the theory part as well as for the practicals. You will have to come to the Department of Geology, where you will have the experience of using this polarizing microscope. So anyway, my name is Sanjeeva Malaviarachi. I'm from the Department of Geology, University of Peradeniya, Faculty of Science. So I'm going to give you some introduction about the optical mineralogy that will be useful for you to understand some gemological concepts as well, because gems are the minerals, a special group of minerals which have some special properties. So before going to the optical mineralogy uh, theory parts, let me uh, discuss with you some special features or some characteristic features of minerals. So if somebody asks you what is a mineral, how can you define a mineral? So I think you have already learned about some preliminary aspects of gemology or mineralogy. So you must be able to give some basic understanding, basic introduction about minerals. If somebody, because being gemologists, some people might ask what is a gem and what is a mineral, what is the difference or something like that. So how are you going to answer them? Can anybody tell me? So what is a mineral? Just, just according to understanding?
Yeah, mineral is a inorganic matter which has a definite chemical composition and also which comprises with physical and optical properties.
Yeah. Okay. So what about a gem then? How do you define a gem? How do you think, how do you introduce a gem for a average person?
Out of those minerals, set of minerals are selected as gems because of their beauty, rarity, and durability.
Okay. Yeah, that's correct. Yeah. So minerals, as you correctly said, should be an inorganic matter, inorganic compound, having a specific chemical composition as well as a crystalline shape. So that means composition and shape is very important for a mineral, to define a mineral. Being definite chemical composition, uh, we might say that the chemistry of the mineral is not fixed also. Okay, that also an important point, but it might be confusing because we are saying that mineral should be having a definite chemical composition, but now I'm saying that it's not fixed also. So can anyone explain a little bit about that? For example, we'll say quartz, right? Everybody knows quartz, right? Quartz is a mineral, very simple mineral, which you can find everywhere, right? Quartz is Tiruvana in Sinhala. So what is the chemistry of quartz? What is the composition of quartz?
Silicon dioxide.
Silicon dioxide, SiO2. Okay. So that means it has a definite chemical composition, right? What about another mineral? Might be, let's say, olivine. Yeah, it is also considered as an as a gem also. So when olivine is considered as a gem, how do you call that gem, particular gem? Probably you have heard of olivine, right? The mineral olivine. Sorry.
Peridot.
That's right. Good. Peridot. Yeah. Why that peridot name came for that olivine when it is considered as a gem? Otherwise, it's just olivine. How that name uh, derived, or how that was named as peridot? That has a relation to the earth. Those who may have read about the earth might be able to answer that question. So in gemology or in gem trade or in gemologists, among gemologists, this peridot is very non-gem variety. But if I mean, if someone says olivine, it might be not very popular as a gem, but both are same. Can anyone guess how this name came? Any idea or any guess? Did you learn about the Earth's composition under this course, under this gemology MSc?
Yes, sir.
Yeah. So you learned. I think you must have learned about the crust, mantle, and core already, right?
Yes.
So one of those layers, right? We call them compositional layers of the Earth, crust, mantle, and core, has some close relationship with this olivine. Which layer? Crust, mantle, or core? Which one has more closer relationship with olivine? Did you learn about the composition of those layers? Crust, composition of the crust, composition of the mantle, and composition of the core. Elemental composition as well as the mineralogical composition or the rock composition. Because all these layers have rocks, right? They are made of rocks, and rocks are made of minerals, right? Either one mineral or many minerals, right? So we call such rocks monomineralic rocks or polymineralic rocks, right? For example, if you take quartz, it's a mineral, right? So just now I mentioned about SiO2, quartz, but the rock which is composed of 100% quartz is called what? What is the name of the rock that is composed of only quartz?
Quartzite.
Yeah, correct. Quartzite. So it's one of the rocks in the crust, right? In the crust we have quartzite, abundant quartzite. And another rock type available in the crust. Can you tell me? Another type of a rock which is common in the crust, in the Earth's crust, crustal layer. Even at your home you can find some people should have used that rock to make some sections of your home to make it
Granite.
decor. Sorry.
Granite.
That's right, granite, right? We use granite blocks for kitchen or for floor, right? Like marbles. Yeah, granite. Yeah, granite is not a single mineralic rock, right? It's a polymineralic rock because it has several minerals like quartz, feldspar, biotite, like mica, like minerals, right? Several minerals are there, so that's why you can see white and black, some combinations of minerals in a granite, but in a quartzite you see only just whitish material, right? That is quartzite only, but very, because in the nature you never find 100% quartz bearing quartzite, right? There are some impurities, maybe some feldspar a little bit, right? But more than 90% are quartz. In granite also you have a lot of other minerals, quartz, feldspar, biotite, like other minerals. So that means naturally a rock is composed of a single or combination of minerals. So that is normal abundant rocks in the crust, right? There are some other rocks also, but just keep in mind those are very common rocks that we find in the crust. So similarly, what do you find in the mantle then? Okay, let's go to the core then before mantle. In the core, what do you find? What are the rocks you find in the core, the most deep part of the rock in the earth?
Nickel
Sorry,
nickel
nickel and iron. Yeah, that's right. But no rocks there. Okay, just elemental nickel and iron is present in the core, but no rocks found because there are no silicate material there, right? If silica is there, then the all these elements will be combined to form minerals, right? Like quartzite, you have silica, uh, just silica only, quartzite, but other mica or other biotite or other feldspars or other things, they have combinations of elements, metal elements plus silicates. That's why they have composed of variable minerals. But in the core, tremendous pressure is there, and also high temperature conditions, very high temperature conditions are there. Silicates are not stable there, so you don't see any silica materials. So therefore, silicate minerals are not present in the core. Most of the silicate materials composes rocks. That's why we call silicate materials as rock forming minerals. Okay, most of the minerals that we encounter in day-to-day life, like quartz, feldspar, mica, pyroxene, biotite, uh, feldspar, and also what else? Hornblende, amphibole. All these pyroxenes, all these minerals are silicates. They are found in abundant amounts in rocks. So that's why we call them rock forming minerals. So all these rock forming minerals are silicates, combinations of elements with a silicate component. There are non-silicates also, right? But majority are silicates in the Earth's composition. Some non-silicates, for example, if you see graphite or galena, right? Galena, have you heard? That is a lead oxide, and sphalerite, zinc sulfide, like zinc. That means uh, they are also compounds, but those are not silica bearing, right? They are not silicates. They may be oxides, they may be hydroxides, they may be fluorides or halides, like other compounds. But those compounds are not abundantly found in rocks. You can find them in rocks in very minor amounts, like 2% or so, less than that even. Therefore, we call them accessory minerals, which are found in rocks. So the most silicates or rock forming minerals, we call them major minerals in rocks. All these oxides and other compounds, like even pyrite, magnetite, rutile, ilmenite, like minerals. They are oxides. Okay, they are not silicates, but they are also found in rocks. But those are not an essential component to make that particular rock. Therefore, we don't consider them as rock forming minerals. Rock forming minerals are the essential minerals which needs to make that particular rock composition. So these non-silicates might be found in concentrated amounts in some parts of the world, some part of the earth, in different places. For example, if you have galena uh, concentrated in one place, for example, in volcanic eruption places, these galena might be concentrated. So in that case, we take them as a economic mineral because that particular locality is rich in that particular mineral. So that can be used economically, extracted, and used for our other purposes, right? For example, graphite. Graphite is also found in rocks in very minor amounts. But if you go to Bogala, there you have concentrated amounts of graphite. So we call mineral deposit, ore deposit, ORE, mineral deposit. Those are economically important mineral deposit. Likewise, such economic minerals can be found in concentrated amounts in ore deposits. So that's a different thing, right? So rock forming minerals and economic minerals are two types of minerals that we find in the world. Out of these all mineral group, gems are special, as you also mentioned correctly. Uh, so coming back to the composition of the earth, now you understand about the composition of the crust and also the composition of the core. So what is remaining is mantle. So what is the composition of the mantle then? What is the composition of the mantle? If you can say elemental composition, then because for the crust, you now know already some light color minerals are there. Light color minerals means quartz, feldspar like minerals. But of course, biotite, hornblende like things are also there. Those are not light colored; they are dark colored. But abundant amounts of light color minerals are there in the crust. So that's why the crust is crustal rocks are sort of light colored. That is also important. But uh, the mantle is different. So now I am asking you about the composition of the mantle. So can anyone uh, give me some, I mean, I don't need exact composition, but just give me some composition of the mantle, some idea.
So basically, partially melted mineral.
Sorry, what kind of minerals?
Partially melted
Ah,
mineral.
okay. Partially melted, not mineral. Yeah, okay, partially melted minerals. Yeah. I'm asking the composition. What kind of a composition should be there? In the crust you have a lot of quartz, feldspar, pyroxene like minerals. That means if you consider their chemistry, the composition, real the compounds, right, they are rich in aluminium. Okay, aluminium bearing phases, not only silicates but also aluminium is also there in considerable amounts. But if you go to the composition of the mantle, aluminium is not that much, but relative to aluminium, some other elements are abundant there. What are those elements? Those are iron and magnesium. Okay, iron and magnesium rich minerals are there in the mantle. So iron and magnesium rich means they become naturally dark colored. Okay, so being the crust is light colored and also light weighted, the crust having aluminium and bearing silicates. But for the mantle, they are having iron and magnesium bearing minerals, of course silicates. They are highly dense, they are heavy, right? Density is higher relative to the crust. And also these minerals are dark colored because they are composed of iron and magnesium, right? So being iron and magnesium rich minerals are there in the mantle, you have a heavy and dark composition for the mantle. Okay, out of those iron and magnesium, magnesium is the most dominant mineral component in the earth's mantle. So therefore uh, magnesium bearing phases are dominant in the mantle, even out of those iron and magnesium bearing minerals. Okay, so olivine is a mineral which contains a lot of magnesium. Okay, of course iron is also there, and iron and magnesium are both composes olivine, but the more magnesium rich compositions are abundant. Okay, so what are the basic type of rock or the most abundant rock available in the mantle? Like granite is available in the crust. Likewise, what is available abundantly in the mantle? The name of the rock type, which is composed of olivine. Majority of olivines are there. Like quartzite makes 100% or close to 100% quartz. Uh, Olivine also makes a special type of a rock in the mantle, which composes more than 90% of olivine. What is that rock? No one knows. I think you must have heard. Yes.
Peridotite.
Yeah, that's right. Correct. Peridotite. Yeah, the rock type is peridotite. This olivine bearing rock like quartzite, the quartz bearing or the quartz dominant rock like that. What you have in the mantle is peridotite. That is olivine bearing or olivine dominant rock. So this is the original name for olivine bearing rock. And since there are a lot of olivines coming out of peridotites, gemology or gemologists or commercial or gem traders wanted to name that particular gem that is extracted from this peridotite as peridot. Okay, that mineral is olivine actually, but people wanted to name it as peridot. That's how this name came for the gem variety peridot. Okay, anyway, so this composition of the earth is also variable, as you now understand. And also I mentioned that mineral is a definite chemical composition, but I said it's not fixed. Why I said it's not fixed is now you understand some minerals are not a single component of a particular element. For example, olivine is a very good example for that. In comparison to quartz, because quartz is just SiO2 only, right? Nothing other than that. But if you take olivine, still a mineral, so it should come under that general definition, having a fixed chemical, having a definite chemical composition. But I said some minerals are not having a definite chemical composition. Some minerals are having a definite composition, a definite chemical composition, but not a fixed composition. So you should understand what is definite chemical composition and what is fixed chemical composition. Okay, some minerals are having uh, a fixed chemical composition, while others are not having a fixed chemical composition, but definitely they are having a definite chemical composition. So what do you understand by that statement? It's a little bit confusing for you, I think. So we will take an example, olivine, for that. Olivine is a mineral which has two end compositions. Two end compositions. Okay, so that means we say olivine has a iron-rich composition as well as a magnesium-rich composition. Abundantly, olivines are having magnesium-rich composition. That is the most olivines we find in the mantle being having magnesium rich composition, right? At the same time, you can have an olivine composition which is zero magnesium. That means they must have iron iron rich composition. So 0% of iron might be there in olivine, as well as 0% of magnesium might be there in olivine. So if 0% of iron is there, that means it's 100% magnesium rich. The opposite is also true. If 0% of magnesium is there, it should be 100% of iron rich composition. So such varieties are also there. So we call them iron rich N member and magnesium rich N member. N member means it's the extreme composition. But naturally, if you analyze an olivine, you will see both iron and magnesium is there in variable amounts, but probably the majority might be magnesium, right? 60% magnesium, 40% iron, like that, right? But opposite kind can also be there. That means 60% iron can be there, 40% magnesium can also be there. But this variability of the composition makes that mineral to have a some kind of a uh, uh, some kind of a varied composition of that varied chemistry for that particular mineral. But the preliminary principle having a definite chemical composition is valid there, because this olivine having variable compositions between iron and magnesium just replaces each other uh, without changing its formula. Okay, it's just keep the formula fixed, but only iron and magnesium is replacing each other. So maybe when temperature and pressure conditions are changing, this replacement can occur, particularly when the temperature changes in the mantle rocks, right? When the mantle is uplifting, right? Uplifting means mantle convection. When the mantle convection is happening, this partial melting occurs, right? So that's how all these magma generates and all these minerals melt, rocks melt. Everything can happen when the partial melting is happening as a result of mantle convection. Okay, so in that time there can
Yes,
be,
sir.
yeah.
Yeah. How does this the composition percentage is changing? Uh, I
Sorry.
mean, how does the say iron composition and the magnesium composition is changing?
Yeah. That you can learn separately actually. But I will briefly tell you what happens in these chemical changes. Actually, this is under the separate subject. Probably you will be learning in the future, which we call solid solution. Okay, solid solution of minerals. So these solid solution minerals are a special category of minerals which you might be touching at the later stages of this mineralogy course, because this iron and magnesium are having a similar size ionic radii. Okay, if you consider the ionic radii, iron and magnesium are having close sizes of these metallic cations. So in places where iron is there, magnesium can be replaced. So this replacement is called diffusion. Okay, diffusion is it's a mobility related thing. This mobility related ionic movement can happen only when the temperature changes, right? Pressure has a very little effect on that, but when the temperature is increasing gradually, iron and magnesium can exchange from they can migrate from one place to another. Having iron and magnesium of cations, both cations of same size, uh, in the mineral, there are places called crystallographic sites. So in those sites only, you have this ionic cation replaced. So for the places where iron is there can be some magnesium replacements occur because of diffusion. Actually, diffusion means when the ionic material move from one place to another, having different contrasting concentrations from high magnesium composition to low magnesium composition. They can migrate when the temperature increases. So that happens. It's exactly like something like when you boil a water, pot of water, right? And you put an ink into the pot, and if you can observe, you can find these ink particles are moving from the initial position to the other places, because high concentration is there in the place where you drop the ink. When you are heating the pot with the temperature, these ink particles are moving to the low concentration areas, to the upper levels where no ink is there, right? So likewise, this ionic material or the ionic particles can also move inside the mineral. So that's why we call it a solid solution, because even though mineral is a solid material, it behaves like a liquid. It behaves like a solution, right? Like if you put some sugar into a tea and you heat it, right? What happens? Gradually, the solution becomes rich in sugar by dissolving them, right? To dissolve them, the sugar particles should move from one place to another place, where from high concentration to low concentration. Okay, so this is a physical phenomena anyway, convection, right? So that happens in the minerals also, but not all mineral can tolerate this process. Only some minerals can behave under this solid solution principle, right? So we will learn about this solid solution later on. So that is how this chemistry changes in minerals. So olivine, when the temperature changes, one type of olivine can be iron rich, and the other type of olivine can be magnesium rich, right? For pyroxene is also this is same. Iron and magnesium matters there in pyroxene. For example, you may have heard the hypersthene, right? Hypersthene is a gem, semi-precious gem, which is a pyroxene, right? This has an average composition of pyroxene. That means 50% of iron is there, 50% of magnesium is there. Still, it is a silicate. The same phenomena applies there. Even for garnet, that is same. It is also solid solution mineral. You know almandine garnet, spacetine, urovite, right? Grossular, right? All these are gem varieties even, right? But they have a different chemistry. That's why they have a different color also sometimes, right? More pinkish, more deep red garnet, or even greenish garnet, even hessonite, that's a grossular garnet. Hessonite, it's a mineral, it's a gem mineral, right? It's a calcium rich. So likewise, all these compositions change in a mineral uh, uh, atomic scale. This happens under atomic scale due to mobility of these cations inside the mineral. Did you get that? It's just a brief explanation. Okay, anyway, so this is how the minerals are having different compositions, and even gems out of those varieties having these special properties like rarity, beauty, and durability. And also, the geologic conditions are also important because to have gems, you must have a specific geologic composition, geologic condition, right? We call tectonic condition sometimes, but in general you can call specific geologic conditions are also required to make those special kind of minerals as gems. For example, what type of gems we have in our rocks? Because originally all the gems are found in rocks. Later on only you can find them in deposits, right? Ratnapura gem deposit is there, but they are not exactly formed in Ratnapura, right? They were formed in elsewhere, somewhere else. Throughout millions of hundreds of millions of years, these gems have transported to Ratnapura from various locations. That's why they are well rounded and very smooth surfaces, right? Not like angular edges, right? They are not having angular edges, they are having a very rounded, very rolled behavior, right? That's because of they have transported else from elsewhere hundreds of thousands of kilometers throughout the geological history, right? So that's how these gems are originally found in rocks and then later concentrated due to various processes. These gems were separated from minerals, from rocks, and concentrated in low-lying basins like Ratnapura. So, what are the main gem types we have found in Ratnapura or in Sri Lanka? What are the gem varieties we can find? I mean, the most precious gems we find in Sri Lanka. What are those?
Sapphires.
Yeah, sapphires, rubies, right? What are those? Those are corundum, right? Corundum crystals. It's a corundum family, either as blue or red, right? Sapphire or ruby. So, what is the composition of that? What is the elemental composition, chemical composition of ruby or sapphire? Sorry?
Aluminium. Aluminium oxide.
Aluminium oxide or alumina, right? It's aluminum oxide. So that means they are not silicates. Okay, so those are not silicates. But rocks have silicates, mostly silicates. But I said some rocks are having some accessory phases. So these ruby, sapphire, they are also accessory phases for the rock. They are not rich in that original rock, but later on they have separated from rocks and concentrated elsewhere, right? They have collected from different types of rocks throughout millions of years time, and now concentrated like a mineral deposit, right? For example, if you want to find uh, mineral deposit, say copper deposit, right? Copper is not common in rocks, right? Copper is found only in abundant in accessory amounts in rocks, but due to various geological processes, this copper can be concentrated as malachite or some other mineral type. They can be concentrated in another place, right? Not in the original locality, right? Then only we can extract them as a economically important deposit, right? So that has happened. So originally this sapphire, ruby have occurred in rocks under very high temperature conditions. We call high temperature rocks are necessary for this for this ruby and sapphire to form, for this alumina to form, right? So that is a special geological condition required. So high temperature conditions, not the high pressure. If our rocks were subjected to very high pressure conditions originally, then we might not have ruby and sapphire in our country. Okay, so that is one implication from our geology, right? Geological conditions. But if you go to Africa, what do you find there mostly? There will be a gem that is not found in Sri Lanka. People come to Sri Lanka to pick ruby and sapphire because those are abundant in our country, and also Madagascar, East Africa, India. There are a lot of ruby and sapphire, alumina, corundum. But if you go to Africa, people go to Africa to find something else. What do you find in Africa?
Diamond.
Diamond. Yeah. Why diamond is there? Because diamond requires high pressure conditions to form, right? Very high pressure conditions to form. So from the deep interior of the earth only diamond can be formed, and that is there in Africa, but we don't see them because our rocks are not undergone high pressure conditions. Our rocks are undergone high temperature conditions, close to 100,000 degree Celsius. But if our rocks can be subjected to very high pressure conditions like 10 gigapascal or 20 kilobars of pressure, then even our rocks can produce diamond. Okay, so for this gem formation, it's very important to have specific geological composition conditions, very specific geological conditions. Okay, so this is one thing related with the minerals. But under our course, we are not much talking about the uh, physical properties of minerals, because we are focusing towards optical properties of minerals. So that is what we learn under optical mineralogy, right? So that's why we have to use a microscope, right? But common microscope or normal microscope, or in other words, as you have already seen them, the biological microscope, where some other biological materials are investigated, is not suitable for mineral identification. Even gemological microscope is not suitable for mineral identification. For a gemological microscope, what you need is mainly magnification, and also to identify the clarity of gems, right? Inside inclusions, fractures, those things you should be able to well seen under a gemological microscope, but not the optical features that you can identify through a gemological microscope. Because under a gemological microscope, you study a non-gem most of the cases. right? Characterize that particular gem, right? To understand how homogeneous this gem is, how the fractures are developed there, or how inclusions are there, like that, right? Even for a stereo zoom, there is another microscope is very similar to the gemological microscope, that is called the stereo zoom microscope. That is also useful, similar to the gemological microscope. But the polarizing microscope is a very different one, because we are using a polarized light beam for observation of the mineral properties. Because under a polarizing the light beam, minerals behave very differently. They give very different colors, very different properties, some very characteristic features. So these features are unique for some minerals. So that uniqueness is used to identify minerals, because in the hand specimen sometimes it's very hard to identify minerals because all look alike, right? Some cases, for example, even olivine and pyroxene, sometimes it's difficult for under the hand specimen to identify when it is at a very small size, right? In a rock, you normally see fine grain minerals, medium grain minerals, and coarse grain minerals, right? Fine grain minerals means mineral grains less than zero point 0.5 millimeter size, right? Medium size means like zero point 0.5 to 1 millimeter like size. So that is a little bit bigger. Even with the hand lens, you might be able to identify. But if it is fine grains, it's very hard, very difficult, right? And also, if you see some physical properties of minerals like color and cleavages, right? I think you have learned about cleavages. Have you?
Yes,
Cleavages, have you?
yes.
Yeah, you must have learned, right? For example, pyroxene, you have some very close to 90-degree cleavage, right? There are some lines like, right? So that's those properties. If the grain is bigger, you can find in even in the hand specimen, right? When you take a sample, right? But you can't find them when it is very small clearly. So in that case, we have to use a optical microscope or polarizing microscope. Then you can clearly understand their differences. And also there are so many other features also. We will go through them one by one for identification of minerals. So basically the use of the microscope is to identify minerals, right? To identify minerals. That means we can't guess, right? I mean, there is no point of guessing in cases where if you need exact name of the mineral, we can say, oh, maybe amphibole or biotite, right? That means it can, once you see a mineral, you can guess it may be a mica or an amphibole, right? Or a hornblende, right? But if you can't distinguish it clearly, then it might not be useful when you want to make it a commercial application also. So then you have to take that sample under a polarizing microscope. If your magnification glass does not uh, give you the clear features for you to identify that particular mineral, then you have to prepare that sample for using under a microscope, polarizing microscope, right? So when you want to determine the rock type, also you have to know clearly clearly the composition of those minerals. Okay, so to determine the rock type, also we need to know the exact chemical composition, exact mineralogical composition of the material. So therefore, we have to observe it under a polarizing microscope. And then sometimes the crystallization sequence is important. What is crystallization sequence? So if you take this partial melting, so you understand the partial melting in the mantle. So partial melting is a sequential process, right? Not at one time all the minerals are crystallized. So they crystallize stage by stage because of different temperature conditions. So at higher temperatures, olivine is crystallized, and then pyroxene is crystallized, and then amphibole, then feldspar, and then finally quartz, like that. So there's a crystallization sequence in magma mainly, right? To understand that also, we have to examine clearly a rock under a polarizing microscope. That is also an important uh, uh, application of a microscope. And also to document the deformation history. So what is deformation history? Deformation, rock layers are deformed. That means that shape is constantly changing due to uh, the geological processes taking place beneath the surface. That means even now, right? Right now, under the crustal conditions, maybe 10-15 kilometers below, right? Rocks are deforming, right? Rocks are changing their shapes. Rocks are formed and layers are formed, and these layers are bending or breaking or folding or faulting. That means breaking and moving, sliding, right? So likewise, there are so many processes are taking place in the earth's interior. Constantly that is happening. Even now it's happening. So when this happen, and then after maybe some millions of years later, these interior rocks are get exposed to the surface, right? So this is a cyclic geological process. So even now you can see in some places where the rocks are exposed, you will see very nicely folded rocks, right? Like you take a piece of paper and you fold it, right? You can make different shapes, right, with a piece of paper. So similarly, rock layers can also be folded and shaped into different configurations. That happens due to tectonic forces available in the earth's interior. And this is happening under high temperature conditions, of course, at crustal depths like 10 or 15 kilometers below the earth's surface. So we don't feel it now, but later on, when the erosion takes place, right, all the top soil is removed by erosion and deposited in somewhere in low lying basins. What happens? The interior rocks are gradually exposing, right? If you remove the earth's soil cap, what do you get? More fresh rocks are exposed, right? So fresh rocks means they are not eroded, right? When the rock is exposed to the atmosphere, only this erosion or weathering can start, right? But as long as they are not exposed to the atmosphere, the fresh rock is remaining. So that is what you call the bedrock, right? If you excavate some place to construct a road, or to construct a dam or reservoir or even a house, right, you will find a good bedrock down there, right? So that rock is there as a fresh outcrop because it is not exposed to the atmosphere. So when with the time, some thousands of years time, right, when the soil is removed by sedimentation due to heavy rainfall or something, then only gradually these rock layers are exposed, right? So this happens over millions of years time, right? So the rocks which are formed at the interior and deformed now today, right, can be exposed to the surface after 100 million years later, right? None of us or even our generations might not be there to see them, but it takes about 100 million years to come them up to the surface, right? So the rocks that you find today on the surface were formed some hundreds of million years ago, right, in the earth's interior. So this is happening, and this history, to document this history, we can use the record available, petrological record available in the rocks. For that, we have to use a polarizing microscope, because we have to investigate different samples from different places at different depths of these rocks under polarizing microscopes, and we can document the history, not only deformation history, but also the crystallization history sequence, and also the mineralogical formation, the mineral reactions even at the Earth's interior. What has happened originally can be traced back, and also you can determine the age, also of these rocks by observations of these rocks under polarizing microscope. So frozen in reactions, that means the chemical reactions that I just mentioned, and also the PT history. PT history means the mineralogical reactions that has taken place at variable pressure and temperature conditions. So that history can also be traced by investigating these minerals under a polarizing microscopes. And also weathering conditions, because also of course the weathering happens on the surface, but you can just look at uh, outside exposure, rock exposure, and check how strong this weathering. Some places you can see very very brownish materials have formed in a rock, but in another place you can see very very solid, like a granite appearance, right? Very hard rock is there, right? That means not weathered. And weathered and not weathered portions can be observed with your naked eye or even a hand lens using. But the micro features, micro cracks, along micro cracks, this weathering has maybe initiated. Even a fresh rock that you find very hard to break, even using a hammer, it might be very difficult for you to break the rock. But if you observe that rock under a polarizing microscope, you will definitely see along some micro cracks there is weathering initiated. So that's how the weathering initiates. It might take another 100 years, oh yeah, 100 years to make it a very loose rock, brownish colored loose rock to be converted. It might take another 100 years or so, right? But now today you might see this initiation of weathering along microcracks. To recognize that, you need a microscope, right? And alteration is also same. Alteration means on the surface the mineralogical reactions taking place, right? Most of the mica are converting to clay minerals. Most of the feldspars are converting to clay minerals, right? So that's why in some rocks you find very soft minerals like clay minerals, very clayish appearance because of this alteration. Okay, weathering and alteration are two things, right? Weathering is just a disintegration of a rock into small tiny pieces, either by physical agents, for example sunlight or wind or temperature variations, frozen conditions can disintegrate rocks, and also chemical reactions can disintegrate rocks. So that is weathering. Alteration is just a surface with oxidation effects mainly, right? Clay mineral formation like processes, okay, in rocks. And also you can see very colorful minerals under microscope. Therefore it may be even fun for school children, right? They see very beautiful colors, and it's a kind of a hobby for a student. It may be to recognize the minerals in different colors, but although they might not be able to recognize what mineral it is, but you can see uh, very colorful places in a rock, right? It's very amazing. Okay, so these are the main uses of microscope, but not the general microscope. Remember, we must use a polarizing microscope because we are interested in mineral properties. Otherwise, it's all right. You can use a biological microscope even. You can check whether there are fossils or whether there are some fungus or something like that, right? To identify those. Okay. Now I am showing you one image under microscope. So this is a polarizing microscope image where you can see different colors. So this is what I just mentioned, that some kids might take it as a fun, because you can see different colors. And also, if you rotate the stage in the microscope, right? So this is a special feature for a polarizing microscope. Also, you can rotate the stage. Other microscopes, today you can check with other microscope. If you go to a lab to check your blood, right? You can see microscopes are used there, but those microscopes do not have a rotating stage. Remember, biological microscopes do not have a rotating stage. Rotating stage is unique for a polarizing microscope, right? So that means rotating feature is also important for mineral identification. Okay, so that means the minerals should be changing their properties while you rotate the stage also, right? So this is one position of at a certain uh, uh, angle. You take this image, and if you rotate the microscope stage, this image will change, right? For example, you have greenish appearance here, right? Green appearance here, and more dark appearance here, right? Like these places. What happens if you rotate this one image, I mean the stage? These colors will change, right? For example, here this light ash colors are there, more whitish appearance is there, right? All these are same minerals, but they appear in different colors, two shades of colors, right? uh, that is as a result of the migrating light under a polarizing configuration. Okay, so that's why this rotating feature is also important to identify these minerals. So when you do the practicals, you can witness all these changes. And even for this pinkish color, you can see here pinkish color, right? And this greenish color, actually these two are same mineral. No two, I mean they are not two different minerals, but only thing is the rotation angle for these minerals are different. The reason is, in a rock these minerals can be oriented in different directions, in different orientations, because they are not just at one direction. Okay, because it depends on the crystallization of the magma, right? Minerals are crystallized randomly, so therefore random orientations must be there. So under a certain angle, they give different colors, because this color is generated due to migration of light through the mineral, right? So depending on the crystallographic orientation, now you should keep it in mind. Crystallographic orientation of a mineral is very important, because that gives out a different color to a same mineral even, right? So you should be able to recognize the same color mineral at a certain angle, and also a different color of the same mineral at a different angle, right? So that is an important feature you can recognize under a polarizing microscope, because the crystallographic orientation is important. Because if one mineral is oriented in a certain degree, because crystallographic axes are there for minerals, right? C axis, A axis, B axis, like crystal axes are there, right? Under crystallography you will learn. I don't know whether you have followed crystallography already or not. Have you?
Yes, sir, we have
Ah,
studied.
okay, okay. Now you know, right? So mineral axes are there. So these axes are different, oriented in different directions during the natural crystallization of mineral, because you can't expect every similar mineral to be oriented in the same direction, right? That happens in metamorphic minerals most of the cases, right? Metamorphic rocks, because they may be subjected to external pressure. So once this external pressure or external forces are applied, differently oriented minerals can be oriented in a single direction. That's why in most of the metamorphic minerals you see some layered structure, right? But here you see very randomly oriented minerals. This is not a clearly oriented rock. That's why you see in different colors the same minerals, right? You will learn about these things in the practicals. Okay, right? Anyway, this is a one image taken by a polarizing microscope, there's a camera attachment there, so we can take an instant picture and save it in our computers under a polarizing microscope. So this is an example taken from a polarizing microscope. So you now should understand there are different colors, some shades of colors, as well as some other features are obvious, right? For example, here this particular mineral, this particular mineral is having some linear patterns, right? Can you see these linear patterns? So similar patterns are there in some other minerals also. So these similar features indicate that all these minerals are one. It's a single mineral, one mineral, right? So we will learn about these features separately, and also you can see here uh, some fractures, right? Some lines. You can see very irregular lines are there, right? Very irregular lines are there. Okay, so these are another some of the another type of features available in minerals, right? All these features can be recognized only through a polarizing microscopes. You can't see these features under hand specimen or with your naked eye or even a magnifying glass. It's very difficult, almost impossible, right? So therefore, these features are very distinguishing features for mineral identification. Even here, you can see this is a sort of a very clear mineral without fractures or lines or any linear features. Nothing is there, right? So only color is there uh, to identify that mineral. Of course, not only color, but some properties can also be used with uh, the polarizing microscope. Okay. Right. So this is the basic usage for the minerals under optical microscope. Always remember, if you are talking about minerals under optical microscope, optical means light microscope, right? So, but for geology or for mineralogy, this optical microscope means a polarizing microscope, where the normal light beam coming from a light source, average light source, any light source is okay. Uh, this light source may be common for a biological microscope also, but it passes through a special arrangement which can polarize this light beam, right? Polarization is a special feature after going through a special apparatus. So this particular apparatus is fixed to the optical microscope. Then only this optical microscope can be called a polarizing microscope, right? This polarizing unit should be fixed to the microscope, and also the stage should be able to rotate, right? So rotatable stage is also very important for a polarizing microscope. Okay, did you get that clear up to now? Do you
Yes.
want anything to be clarified further? I'm still doing very basic introduction only. We will go through little by little.
It's clear.
Okay, right. Now let's see a petrographic microscope or polarizing microscope. Some different names are there. Petrographic microscope or polarizing microscope. This is same. Okay. Actually, it's an optical microscope, as I said, because we are using a light source. So you can see here a light source, and this source gives out normal light, right? Normal bulb is there. So this light comes up to the some special unit here. This is the special unit which is called lower polar, right? Actually, this is the polarization unit, right? This is the polarization unit, and when the light is coming out of this light source, first go through this polarization unit, right? Then what happens to this light? This light becomes a polarized light beam. Normal light beam is converted into a polarized light beam by this polarization unit. Actually, why you call it lower polar? because it is located in the lower side of the microscope, and another polar is located in the upper side of the microscope also here. This is called upper polar. We'll see why we need another polar or another polarization unit later on. But just remember, uh, this is the first requirement. You need a polarization unit, first of all, to get the polarized light. And when this light comes up, there are so many units. We will take up them gradually. But I'm just taking the basic route of the light. So light is coming from the source and passes through the polarizer, and then it enters the stage. Stage is here. This round surface is the stage, and on top of the stage you have the sample here. So this is the sample. The rock sample is here, or the mineral sample is here. See, this stage is here, and this you can see some rectangular whitish material. That is the sample which is placed on top of the stage. And this light beam comes to this sample here, and on the sample you have minerals, right? That is our mineral sample, and this light should be able to pass through the sample. So that means you should be able to make your mineral able to pass the light through it. So if you take some very thick mineral, if you take a very thick piece of rock, if you use a torch and face it to the beam, can you see the light passing through that rock chip? Never, right? It's too thick to pass the light. So sample preparation is very important. For observation under optical microscope or a polarizing microscope, you should have a sample which is able to pass the light through that rock. So how can you make a rock which is able to pass through the light, right? For you think of just a plastic foil or a polythene that can pass light. So that means you have to make your rock into that thickness, understand, to pass the light through it. It's like a very tiny onion peel like, right? Very tiny thickness. Actually that thickness is 0.03 micrometer. 0.03 micrometer. Okay, that thickness you must make your sample. So special sample preparation is required. So such samples are placed on this stage so that the light can be passed through. Actually even thicker than that 0.03 thickness can pass light, but the standard thickness globally taken is 0.03, because when you change the thickness, your mineral properties will change. You saw here this greenish appearance of this mineral will be there at 0.03 thickness. This ash color or this brown, this dark ash color or this pinkish color is available only at that thickness. If you make it more thicker, this green color becomes more brighter. Okay, it may be very deep green, like it's not the comfortable green that we are used to for identification of mineral, because uh, since this thickness can change its optical properties, we have to come up to a certain standard so that we can fix, okay, this particular color is for this particular mineral, this particular feature is for this particular mineral, like that. Because if you make it 0.5, then you might appear olivine like pyroxene, right? Because their colors can be changed. So if you make everything 0.03, then you define these colors. Okay, for pyroxene, this color, for olivine, this color, for other minerals, that color, like that. Then you have a standard, right? So then you must be able to recognize them under the microscope easily. Otherwise, it's very hard because at various thickness, various colors will be there for same mineral. Even you can't identify the same mineral at different thicknesses because the same mineral will be giving you contrasting colors at different thicknesses. So thickness is also important there. So sample preparation is a different thing. We will teach you how to do that in the lab. And maybe you can see how samples are prepared. Okay, we need a rock cutting machine or lapidary equipment for that, and then polishing and making it to that 0.03 micron thickness. Okay, right. So when the light passes through the sample, it enters this lens. This is a lens we call objective lens, right? It's the first lens where the light enters into when light is passing through the source. After this objective, the sample is magnified because it is a lens, and it gives you a magnified, uh, enlarged view because our purpose is to make everything larger. Otherwise, there is no point of using a microscope, right? The first requirement for the objective of a microscope is the magnification, right? If you can't make it enough magnification, there is no use. So then you have to change the objective lens. You need to make a bigger objective with a bigger magnification. So there are several lenses. So you can see one here, another here, another can be in behind, right? So likewise, there can be 3 or 5, even some cases, lenses, objective lenses, which is also rotatable, right? So this unit as a whole, this unit can be rotated so that you can switch between these objectives. If you feel that this is not enough magnification, then you can change for a higher magnification. You can just rotate it with your hand. You just rotate this unit and fix this lens here, right? You don't need to remove the lens, but you can just rotate it and just fix it. Okay, so likewise you can change magnification, and when the light passes through this objective lens, it straightforward enters the upper plate, upper polarizing unit, the second polarizing unit. It enters through upper polarizing unit. Okay, and there are some other equipment or other components as well. I'm not explaining them now, right now. These are optional things, right? These optional things I will later inform you. And when the light passes through this upper polar or the upper polarizing unit, then it goes to the ocular. Ocular means the eyepiece, right? You know, eyepiece, that is where your eye is placed, right? Through this only you see the sample. So you will see an image of sample when through this eyepiece, since your light ray from starting from here travels through this objective and then comes to this place, to this lens, right? So the magnified image will be further magnified by this ocular, by this eyepiece, because eyepiece is also having a typical magnification of 10 times, right? So whatever the image you are magnified image you are getting here will be magnified further 10 times by this eyepiece. Okay, so usually these objectives, the first objectives, lenses, which can be variable from 5 magnification, that means 5 times than the normal size, 5 times than the sample size, 10 times, 40 times, 60 times, like that, or even 100 times. That is the maximum magnification obtainable from objective lens. When it comes to the eyepiece, it will be further magnified 10 times. That means if you had used the 5 times magnification here, objective, you will get an image here 5 times bigger. But when it comes to the ocular or the eyepiece, further 10 times magnification will be available. So that means 5 times will be magnified into 50 times, 10 more times, right? So likewise, you can have a continued magnification when you see the sample actually through your eyes. So here you are observing the sample, you have a large magnified image seen here. So even this image is a magnified image. I think this is about 400 times or at least 100, yeah, more than 100 times anyway, right? I don't know what objectives they used, but this is a largely magnified image compared to the sample. So 100 times magnified or 400 times magnified means, or 500 times magnified means, you can observe very, very tiny features of the sample, which are never observable through your naked eye or even using a hand lens. So that is the basic objective of using this uh, microscope, polarizing microscopes. Okay, so for a polarizing microscope, the necessary equipment are light source, polarizing unit, stage, and the ocular, objectives and ocular. Okay, this upper polar sometimes we use and sometimes we do not use. So that means you can use it as an optional component as well. But frequently we will have to use it. Therefore, we may take it as a uh, regular component of the microscope, not as an optional component. But only thing is, you can remove this upper polar from the image, from the light path. If you want, you can insert it, and if you don't need, you can remove it. But this lower polar is fixed, permanently fixed. You can't remove it. So if you remove it means your microscope will be simply converted into a biological microscope. Okay, we must have this lower polar fixed permanently to the microscope. Uh, that is the polarizing unit, first polarizing unit. Actually, this is the second polarizing unit. Okay, which is not necessary always. When you need only, you can put it. That means it's a sliding component. You can slide it out and slide it in to the microscope. But this is not adjustable. It's fixed. Okay, so these are very important components of the microscope, of the polarizing microscope. And the stage is usually is rounded. Okay, it's usually rounded because it's a graduated stage. Graduated means the angle is there, 360 graduation is there. Okay, 0 to 360, because this angle is important, because I said the rotation is important, right? When you rotate the sample, these colors change, these features change, and sometimes we need to know how these changes happen at a certain given angle, right? So for example, you have this very bright whitish appearance of this mineral. It can be at a certain rotation angle become something like this dark color. It can convert into dark color when you rotate the stage. So you should be able to know at what degree this conversion took place from bright to dark. Change maybe how many degrees you had to rotate it, 30-degree or 40-degree, 45-degree, like that. So that particular feature is also important to identify the minerals, because that change is different from one mineral to another. One mineral may be 30 degrees, that bright appearance to dark appearance, but another mineral, it might be 60 degrees, right? So that alone gives you a unique feature to identify that particular mineral. Okay, for feldspar it's different, for quartz it's different. So using that angle, you can realize, okay, this is not feldspar, this should be quartz, because for feldspar it should be 30 degrees, for quartz it is 60. Now I rotated it like almost 59 or so, right? Then you realize that, okay, this is a special optical feature which distinguishes quartz from feldspar. So likewise, such features are very important. That's why we need this rotatable stage for a polarizing microscope. Okay, so this is very important, and stage is very important. So these are the basic requirement for a polarizing microscope. So optionally, you can have some other lenses also fixed into this. You have one lens here called Bertrand lens. So this is again an optional thing. That means you can slide it out. If you don't need, you can slide it in if you need it. Right? That also gives you some optical property. We will see them later on. Okay, and there is another thing called accessory plate. This accessory plate is another kind of a lens-like thing. It's actually not a lens; it's a plate made of some special material like calcite or something. When you insert it, your image, your image you show here will be converted into a very different color, right? But that different color also gives you some implication, not for every mineral, but for some mineral. So that can also be used as an optical property to identify when you need to use an accessory plate with your microscope. Every microscope do not have this accessory plate because these are optional things. Some microscopes come without this accessory plate, without this Bertrand lens also, right? Uh, but for identification of basic properties, these are not necessary. Okay, that's why they are optional. And objective is must, stage is must, and goniometer is calibrations, graduations along the stage. You can count how many degrees you rotate this one, clockwise or anti-clockwise, like that. And there is another thing called auxiliary condenser. There is a condenser unit here. This is also not necessary, but very useful. If you are having it, it's very useful. Being a condenser, it actually it makes the light beam condensed to one spot. Okay, so this light beam, if you condense it to a particular location in your sample, right, that's also very useful for some situations. So therefore, in that case, this auxiliary condenser can be used also, right? You can make it in or make it out from the light beam as an optional component. Then condenser unit has a lens, separate lens that makes this light beam condensed, right? That facilitate this one. So that is the lens, condenser lens. And there is another one which is not marked here actually. There should be some lever like here, a small lever, right? Rotatable lever, movable lever that we call diaphragm, right? So with that lever, we can, we have a tiny diaphragm, tiny, very thin layer of transparent layer, right? That also makes some requirement when you observe some minerals. If you, it's like a filter like thing, right? It's like a filter, right? You can apply that filter or remove it, right? For different purposes, but those are optional. So this is having those component, and also you can see here a knob, a big knob and a small knob, right? This is a big knob and this is the small knob. Actually, this is used to change the stage level, right? Actually, for focusing, because you know you have an objective lens here, you have a sample here, but not for all samples you fit this length, right? This focal length. To change this focal length for focusing purpose, you can use this knob. This is rotatable, right? When you rotate this one, stage moves up and down. Stage moves up and down. If you rotate one direction, it moves up. If you rotate opposite direction, it moves down. So within this working space, within this space, you can move the stage up and down so that you can get the best view, focused view, right? So this tiny knob gives you again a kind of a focusing, right? We call it fine focusing, right? It also moves the stage, but very little, right? Very tiny amount, because when you move this stage by this uh, uh, big knob, stage is moving rapidly. But if you move this one, the small knob, the stage moves very, very little. Because once you take up your sample into a certain focal length, fine focusing can be done using this one with this tiny knob, right? Small knob. This is also rotatable. Okay. So these are the main components of the microscope. So this part you can call the base of the microscope, where you have a switch, on off switch, the light source. Previously we had a mirror here, mirror fixed for the light source, because we use the sunlight. You get the sunlight from here, and that mirror reflect the light to the sample. Old microscopes, right? But now what we have is a bulb, electric bulb is there. So that bulb gives out light uh, nowadays. So for that you need a switch in behind, electric switch there, that is also located in the base. And this part is called the body of the microscope, the body. And this entire thing is the body, and this part is called head of the microscope. Okay, these are removable parts, because for repairs you may need to remove these parts, and also to clean the lenses you may need uh, these uh, parts separated from the microscope. Okay, so this is the polarizing microscope, which is different from a normal microscope. Okay, normal biological microscope or normal other light microscope. So how they differ, you should understand how they differ. How they differ from a normal microscope, a polarizing microscope, having what?
Use polarized light.
Yeah, usage of polarizing unit, and also the rotatable stage. Those are the main differences compared to a biological microscope. Okay, so to use the microscope, actually we need to understand some little facts related to physics. That means the migration of light through the lenses, right? So we may need some basic understanding of light beam traveling through lenses. That means optics, right? But you don't need you don't need full physics knowledge for this one. Just some o-level physics, o-level science knowledge with respect to light beam migration or light beam propagation may be enough. Okay, but for deep understanding you might need a-level physics, but it's not necessary at this stage. Okay. Right. So, any questions up to this level? Do you have any questions? So, actually, there are different brands of microscopes, polarizing microscopes, petrographic microscopes, or petrological microscopes. Sometimes we call petrological microscopes also, because having this view is very important, right? This view is very important, because we have to sometimes we have to select uh, these tiny grains, even some tiny inclusions, right? You see here some black spots, those are inclusions of minerals, very tiny inclusions, very micro level. You never see them without a microscope, right? Sometimes you can realize what components or what mineral reactions that cause this mineral to form, right, using these inclusions. Those are very important for identifying those. This microscope, polarizing microscope is a must. You may see some very tiny grains like zircons, right? Some zircon grains you may see. I don't know whether you have anything here. This magnification is not enough to find out tiny zircons. Some zircons might be 100 micrometer size, and that micrometer size zircon can be used to date your rock. That means for age dating, because zircon is the one, the mineral used for age dating. So this is very important. So we can use even this tiny section of the rock, we call a thin section Okay, because we have polished it so that it gives a very very thin thickness, very thin, 0.03 micrometer. Okay, so that zircons can give you the age of the rock. We can take this thin section into another equipment, and that equipment can give you some isotopic analysis. We will talk about them later, to give you the age of the rock, right? The age of the planet, how much? 4.56 billion years, right? So that age is also taken from a zircon grain. So we can find out how old our rocks are, right? Any guess for our rocks? Anybody has any idea about the age of our rocks? Many zircons from our rocks have been used for age dating. Do you know how old our rocks, at least? The rocks that you find in your garden might be having this age, because most of the rocks in
Four,
Sri Lanka. Sorry, yeah.
4 billion years,
How much? But I didn't get you.
more than 4 billion years.
4 billion, you mean? Age of the Earth is 4 billion. That's okay. 4.56 billion years. What about the rocks that we have in Sri Lanka? Do you think they are as old as that age?
What is,
Where do, do you know where this 4.5 actually 4.5 billion years old rocks are not yet found in the planet, but 4.4 or 4.2 billion years old rocks have been found.
yeah,
Where?
that's right.
Yeah, where those rocks were found?
I think Gondwana is 500 billion. Sri Lanka is 500 billion. Yeah.
Yeah, that's correct. uh, our rocks are around 550 or 500 above. Okay, 500 million years above, right? There can be some 2.8 billion years, 2.8 billion, that means 2800 million years old rocks also in Sri Lanka, but not older than that. I mean, maybe 3000 million years maximum. Okay, very rarely. But 2.5 to 2.8 is common in Sri Lanka, and 500 million years is the dominant rock age of our rocks. Uh, about 4.3 billion years old rocks, that means 4,300 million years old rocks. That is those are the oldest rocks in the world, in this planet. Were found from where? That's general knowledge, not geology. From where? They were also dated from zircons. They were found from Jack Hills in Australia. Okay, Jack Hill Mountains. Those rocks were very old. Previously, the oldest rocks, non-oldest rocks were found from Canada, Acasta province in Canada, about 3.8 billion years, 3,800 million years old. Later on, these Australian rocks were found. Now, the oldest rocks in the earth are from there, from Australia. Okay, so our rocks are ranging from 550 millions, or more or less 500 million years old, and they can be extending even up to 2,800 or 3,000 million years, right? Our rocks. So we will learn about the Sri Lankan geology also separately. I think somebody else will be teaching you. So anyway, so we will continue with these petrological microscopes or polarizing microscopes with the next class also. Okay, so for today I am going to stop here. So I think uh, do you have any questions? So we have few minutes. If you have any question, I can answer, or otherwise you can pose the questions if you by email or at the next class also, right? I hope everyone recorded your name and number in the chat box. Have you? So today we had only 10 or 11 participants. So if you are more than that, please ask them to join, because this part is not easy. I mean, some new concepts are there, so that is, it should be very well understood. Otherwise, it's difficult to go ahead with the practicals. Okay, so please ask them to join at the next time. Okay, we'll stop here for today. Okay, thank you for joining.
Thank you very much, sir.
Okay.
Thank you, sir.
Thank you,